It's fun to imagine scales and stars. The most efficient method of attempting to understand the most inconceivable aspects of science is to use analogies. Consider the size of an atom. So how big is an atom exactly? To be precise, the diameter of an atom measures between 0.1 and 0.5 nanometers. That's 1/1000th of a meter. But how small is that?
Let's think of it like this. The scale of an atom to an apple is the same scale as an apple to Earth. Likewise, one atom is 1,000,000 times smaller than the thickest strand of human hair. These numbers can be very difficult and frustrating to imagine. Over time, one can get exceptionally exhausted trying to visualize the scale of an atom compared to us humans. In astronomy, we have a similar situation, but in reverse.
Thinking about how far away our galaxy is and how many stars it consists of is an extremely difficult image to describe. The mind-blowing scales of which stars' distance and size are on cannot be compared to humans on Earth unless told from a different perspective. The distance to the nearest star is inconceivable. Putting things into perspective, light travels for about 3 years until it reaches the nearest star that there is to us. To make things a little bit simpler, let's talk about the speed of light.
The exact speed of light is 299,792,458 meters per second. But how fast is that? What does that number mean, and how can we understand it? Basically, light travels so fast that it only takes a few seconds to go to the moon and back. Light can go around the Earth 7.5 times in 1 second. Consider how long it takes to get over the Atlantic Ocean by a plane. For us, that's a little over 15 hours. Now imagine going around the world almost 8 times within 1 second.
The speed of light is something ordinary people have a hard time getting used to. The thought of humans being so incredibly small on the scale of our galaxy is confusing for many people. Higher on the scale, stars and galaxies thrive. Let's get a better understanding of what stars compose. A galaxy is a group of an enormous mass of stars. To grasp the size of these galaxies, we can refer back to light years.
The Milky Way is about 100,000 light years in diameter. From there, it takes 1,000,000 light years to reach the nearest galaxy, the Andromeda Galaxy. Meaning, the distance between galaxies are 10 times more than their size. But what is a light year? Is it a measurement of time?
Actually, a light year is a unit of distance, equivalent to the distance light travels in 1 year, which is numerically about 9.5 trillion kilometers. To help you imagine the distance light travels in 1 year, consider 1 trillion in terms of seconds. 1,000 seconds is equal to 17 minutes. 1,000,000 seconds is equal to 17 days. 1,000,000,000 seconds is equal to 31.7 years. And finally, 1 trillion seconds is equal to 31,709 years.
This should help you understand, or at least begin to imagine, how great 1 trillion really is. Now, multiply that amount by 9.5 and consider it in kilometers. You now have 1 light year. By thinking proportionally, we are able to understand large distances and enormous masses. Learning in different perspectives allows us to comprehend the insignificance of us compared to our galaxy.
Have you ever wondered why the Earth is round? It is because the constant force of gravity is pulling the Earth's surface towards the center of the Earth, creating a sphere. Mountain ranges are areas where the force of gravity isn't strong enough, so we have bumps. Mount Everest is the Earth's biggest bump. This explains how the ridges on the moon are higher, because the force of gravity on the moon is weaker than the force of gravity on Earth. Objects with more mass have more gravity. Therefore, the moon exerts a stronger force of gravity. However, gravity also gets weaker with distance, so the closer objects are to each other, the stronger their gravitational pull is. Now let's relate this information to stars.
Stars, basically, are luminous balls of gas, mostly hydrogen and helium. Stars are held together by their own force of gravity. We only see about 5,000 stars at night. However, there are so many stars in our galaxy alone that if you tried to name them all, one per second, it would take you over 3,000 years. When you look at a star through a telescope, the light seen is spread from the star over an enormous distance of 3 light years. As the light from the star spreads, its wavefront gradually gets wider and weaker. It travels through all of space until it reaches our eye as a tiny white glimmer, which is all the proof we have of its existence.
Now, let's talk about the most famous star of all, the Sun. The Sun basically is a huge mass of hydrogen that is held together, like Earth, by gravity. The Sun possesses nuclear fuel which burns continuously, generating energy. There is a possibility that if we push any mass closer together, and the gravity is stronger than the pressure induced by the applied force, it would hold together. Let's investigate.
If we push a little bit, the gas atoms pound and mend together, increasing the pressure. If the gravity is stronger, the pressure wins and the star oscillates. If you continue analyzing and push the mass even closer together to the concentration of, for example, the mass of the Sun transforming to the size of the Earth, the atoms get very close together. The nuclei atoms become so close and condensed, which increases the force of gravity. Gravity strengthens enough to overpower the pressure and is able to keep the thing steady. At this point, the thing has transformed its shape and size to be nothing but solid nuclear matter.
This theory was imagined by physicists J. Robert Oppenheimer and George Volkoff, and is known as the theory of the neutron star. The existence of the neutron star has been proven. The star spins rapidly, simultaneously emitting a beam of light, which we have yet to understand, but we can always imagine. The idea of a neutron star is that there could be a star of such an enormous density that a teaspoon would weigh so much that if you put it on the Earth's surface, it would plow right through to the center of the Earth. A teaspoon of a neutron star material would weigh about 10 million tons on Earth.
In science, we use our imagination to imagine things that have the potential to be in our reality, but may not be. Particularly in astronomy, imagination is necessary to estimate what kind of structures and occurrences happen within stars to produce light, and how that light travels to our eyes. Ultimately, our imagination is an extremely useful concept, which allows us to better explain things we can see as well as the things we can't see. And it's fun!
Thinking about how small we are compared to the universe is very daunting, but it's less depressing if you consider how big we are compared to atoms. As frustrating as the universe can be, instead, take the time to relax, enjoy, and appreciate the complexity of our universe. Thank you.